This set of notes is about electrolytic cells. Set of notes has been provided to you in Schoology. You know the drill. Right, so for our topic today about electrolytic cells, we have to go back and we have to just once again review. We know that delta G for a redox reaction can be found by using the equation. Delta G equals negative NFE. So again, that means that a negative delta G means that we've got negative thermodynamically favorable. That happens when we have a positive voltage, thermodynamically favorable. It's not thermodynamically favorable if delta G is positive, which would mean that we would have a negative E. Delta G is equal to 0 at equilibrium. Therefore, the cell voltage is 0 at equilibrium. So thus far, the cells that we have looked at or talked about are favorable and they generate electricity. We call them voltaic or galvanic cells. And they are a situation where we have the voltage is positive, which means delta G is negative. That means that Q is less than K. And so therefore this thing is overall favorable. Okay. In this particular situation, we're talking about a real life practical application of this being batteries. This is how batteries work. Okay, but what about the opposite, non-spontaneous or not thermodynamically favorable? Well, we refer to these cells as electrolytic cells. Electro means electricity. Lysis or lytic, it means division. So this is division of things using electricity is where it gets its name. And of course, the quantitative description of these is the opposite of voltaic or galvanic cells. We have a positive delta G because it's not spontaneous or not thermodynamically favorable, which means that the voltage is negative, meaning we have to put electricity into it, and Q is going to be greater than K. Okay, so we've got this particular situation. So in order to be able to do this, you have to use outside energy to drive this reaction. Okay, so uses, where would this come into play? Why would you ever want to do this? Well, one, are rechargeable batteries, right? Over time, the voltage of them dies and gets lower and lower, and eventually it goes dead. When we want to recharge it, what do? Well, we got to reverse the redox reaction to regenerate the chemicals that were in it to begin with, and so that it can run again. We can use this to produce pure metals and gases. So if I have most metals and gases are originally found in compound form, minerals, things like that. And if we want to separate them out, one way of doing that is taking them from their compound form, where they're in ionic form, and running electricity through them to do reduction, which then generates the pure metal or the pure metal gases. They also use this, if you've ever heard of something being gold plated, this process is used in plating metals. All right, so in an electrolytic cell, it's set up a little bit differently than a voltaic cell. But the first one commonality that they have is you still have two electrodes connected by a wire. You have the cathode, which might be related to what you're trying to oxidize and reduce or react, or not. Okay, but reduction still happens at the cathode. So red cat still works here. Okay. Anode, again, is where the oxidation happens. So anox still works here. And once again, that can also be related or not related to whatever substance you're trying to react. Third thing that you need is you need either a molten salt, so an ionic compound like sodium chloride that we melt into a liquid. Again, when salt melts into a liquid, it's going to separate into its ions, Na plus or Cl minus. That also happens in an ionic solution, so that would be another way of thing that you could possibly have in your cell to be able to do an electrolytic cell. Right. Then what you need is an electricity source on the wires. In this particular case, they have a battery. Probably need to be a fairly strong battery, unless it's a weak reaction, then you maybe wouldn't. But that electricity source, whatever it is that's providing electricity on the wire, has to provide more energy than the cell potential would. Okay, so whatever this the E cell of the reaction is, you have to give it more electricity than that in order to make the non-spontaneous reaction happen. So we're coupling production of electricity, which is spontaneous, with using that electricity to do something, which is non-spontaneous here. Okay, so the electron, what does the electricity do? It basically overwhelms the electrons and says, hey, we're providing you with electricity, lots of negative charge. And so that forces the electrons in the opposite direction that they would normally go. In other words, they move toward the cathode, which then becomes negative, and away from the anode, which is positive. That's a sign difference from our voltaic cells. All right. You'll also know here that we do not need a salt bridge. Remember, a salt bridge in a voltaic cell is used to keep the charge balanced so that the electrons can keep flowing. Well, we don't need that here because the electricity source is what keeps those electrons moving through the wire. All right, so let me show you an example, okay? An example of using an electrolytic cell in this particular case to do electrolysis, okay? To separate a chemical using electricity. All right, so in this particular case, the chemical that we're going to separate is sodium chloride, our molten NaCl, and we're going to separate that into sodium metal as a liquid and chlorine gas. All right, so if I go ahead and I write the half potentials for this NaCl, again, in its liquid form, is going to separate into Na plus and Cl minus. So our half reactions are the Na plus an electron goes to the elemental form of sodium. If I look that up in a table of reduction potentials, the reduction potential for that particular reaction is negative 0.271. And you'll notice in this particular case, because of the way that we're going here, we are reducing this because we are adding an electron to it. Okay. Next, we have chlorine. The part of this is the chlorine ions will change to chlorine gas. In order to do that, we need to add an electron. So this one is going to be our oxidation. Okay. So our oxidation here is going to be our reduction potential for that particular reaction is 1.359 volts, but it's not the reduction that we're doing here. We are doing the oxidation. So we're going to flip the sign on this. Okay. If I then take those two and I add them up, negative 2.71 plus negative 1.3959, we get a voltage on this system of negative 0.407 volts. Well, we know that that's not a favorable, thermodynamically favorable reaction. So what do we need to do in order to make this reaction go? We need to supply it with a battery or a power source that is at least as big, or that is bigger than that E cell that we see right there. So as long as my battery is providing more than 4.07 volts, the reaction will continue to go, and our electrolytic cell will produce chlorine gas and sodium metal. You'll also notice in the cell, reduction, the sodium is still turning into sodium liquid at the surface of the cathode, and the reduction or the oxidation is still happening at the anode, and that's why we see these bubbles of chlorine gas coming up. Okay. Another example of electrolysis, the electrolysis of water. Okay, so 2H2O goes to 2H2 plus O2 gas. You think about this in terms of oxidation numbers. We're going to get hydrogen ions going to hydrogen gas. So that is being, electrons are being gained. There's our reduction. Okay, and we have oxygen going to oxygen gas. And we've got electrons being lost there, so there's our oxidation. Same process, though. We could figure out what the amount of current required to do that actually is, and as long as it's bigger than the reduction potential or the cell potential of that overall reaction, the water will separate into hydrogen gas and oxygen gas. Okay. Another example, copper chloride. Okay. It's changing into solid copper and chlorine gas. Okay, half reactions for this. Copper ion plus 2 electrons to solid copper. Again, for that particular case, we are gaining electrons, so there's our reduction. Chlorine plus goes to chlorine gas plus 2 electrons. Electrons are being lost, so there's oxidation. Once again, the battery or the current source would need to have a voltage that was greater than the voltage of this cell. Okay. So in the previous situations that we showed you, we had some situations where the thing being going through electrolysis was a molten solid versus a aqueous solution. Okay, the last one we showed you was an aqueous solution. Well, if you use a solution that is aqueous and not a molten salt, what will oftentimes happen is it will oxidize or reduce water instead of one of the ions, okay, because of the difference in reduction potentials. So the water will either have a lower reduction potential, and so it will get reduced first before you get to the thing that the ion you actually want to reduce out. Okay, so once again, this happens if water is more easily reduced than the species that would be reduced in the reaction. In other words, if it has a more negative potential. And or if the oxygen is more easily oxidized than the ion that would be oxidized. Okay, so doing electrolysis with a solution of an ionic compound doesn't always result in successful electrolysis. You have to have ions that are reduced more easily or oxidized more easily than hydrogen is reduced or oxygen is oxidized. All right. That's it. That's all you need to know about electrolytic cells. Have a good one.